Hi guys, I'm going to be going over just some basic intro to forces stuff. I'm creating this for like all levels of physics, so I'll kind of try to tell you when something is an AP physics level, honors, and advanced, and so on. So just for now, assume everything is for everybody unless I say otherwise. So starting off, what is a force? A force is a push or a pull. It's that simple, and a lot of my students are like, wait, shouldn't there be like a scientific definition? And that's kind of it. It's just an interaction between two objects, and it's a push or a pull. There does need to be two objects. Some of my students think that you can push yourself, but that's just one object, yourself, right? And that's not possible. So in order for there to be a force, there has to be two objects. So yourself and the ground, or a golf club and a golf ball, or your hand and literally anything else. Some other basic things, the units for force are newtons, named after Sir Isaac Newton, and that is a capital N for newtons. And the last thing, and this is for the I guess advanced honors and AP, force is a vector quantity, and we'll talk more about vectors later, but basically all you need to know is that force has direction. That guy in the video there, that GIF, he's getting punched from the left to the right, but somebody could be on the other side punching him from right to left, and that would be a different direction with a different force. So force has direction, and that's all we mean when we say vector quantity. Now I'm going to get into the different types of force and what we call them. So at the top you'll see gravity, it says, and then it says in parentheses capital F with a subscript lowercase g. That is, that's the name of the force, and then also the variable that we use, or the label that we use to call something the force of gravity. Now it's very important that you label things correctly, because if you don't, then we might get confused on what kind of force it is. So all forces are capital F, and that subscript just tells us what kind of force it is. So in this case you see a little g, and you know that that means gravity. Now gravity is a field force, and a field force is just something, it's a force that can act through space. It doesn't need to touch what it's acting on. So, you know, if I want to exert a force on this pen, I have to push on it, I have to touch it. I can't just like exert a force on it without touching. I'm not, you know, a superhero or anything. But gravity actually can exert forces through space. I mean, right now, gravity of the Earth is exerting a force on this pen, because if I drop it, it falls, so it must be feeling that force, but yet, you know, Earth is not touching the pen. So that's what a field force means. Now, the force of gravity is also more commonly called weight. So if you're saying, you know, I weigh a certain amount, we're really talking about the amount that the Earth is pulling on you. There's also an attraction between all masses. That's really where gravity comes from. Mass in general, and by the way, mass is just matter, so like stuff, atoms, anything that's made up of atoms, which is, by the way, everything except for like light and weird stuff. But anything that you can think of really is attracted to something else. So this pen and my finger have a certain attraction to them because my finger is made up of mass and the pen is made up of mass, and they attract one another. The only difference between talking about everyday items, or even like, you know, not on the planetary scale, is the fact that these forces are so tiny that we can ignore them. They're really just negligible, which is the fancy word for just saying that you can ignore them. So again, there is an attraction between any object, any two objects that have mass, which is any object. It's just that those forces are so small that you can't really tell. On the surface of the Earth, gravity always points downward in our perspective. If you zoom out and you go into space, and you go deep into space, gravity doesn't need to point downwards, but then again, which way is up and which way is down in space anyway? Right? So, moving on from that. Magnetic and electrostatic forces. These we're not going to learn about until later in the year, but magnetic is a capital B for the subscript, and if you're like, why isn't it M? Well, M is for mass, so B is for magnetism, just because. And electrostatic is E. These are also field forces, meaning that they do not have to touch in order to exert their forces, and these forces come from electrons. So every atom is made up of at least one proton and one electron. Actually, that's not necessarily true, but most atoms have protons, neutrons, and electrons. And the electrons have these, and protons have these attractions or repulsions based on just how they are. Again, we're not going to get into this very much, especially right now, but all you need to know is that they're field forces, and magnetic forces come when you have magnets or electromagnets, and you guys are pretty familiar with those, or and electrostatic forces come from when you have static electricity. So you guys know when you rub your socks or you pull off a sweater, that's static charge. Those can exert forces. You can like make your hair stand up with electricity. Friction. Whoops. I don't know where my friction thing is. Friction is a contact force. So we're talking about two surfaces rubbing against each other. There it is. Friction always acts opposite of motion or would-be motion. And it's always parallel to surfaces. So if you look at the very bottom picture there, that's what you would see if you zoomed in on any two surfaces. Even the smoothest surface you can think of, if you zoom in on it, you would see that they're made up of nooks and crannies. And those nooks and crannies, as they skip across each other, are exerting forces on one another. And those tiny little micro forces add up to one big frictional force. And friction can only act parallel. So right now, if you look at that picture of the two metals rubbing against each other, friction can only act left and right. The friction in this case cannot act up and down. So they only act along the surface that's rubbing against each other. We're going to learn more about friction later and dive deep into it. Normal force. The word normal actually means perpendicular. And perpendicular, it just hints towards the fact that normal force always is perpendicular to the surface. So friction is parallel to the surface, normal is perpendicular to the surface. And it's also a contact force, and it arises from two surfaces. And normal force is the reason why things don't fall through other things. So if we put something on the table, the reason why that object doesn't fall through the table is because the table is pushing back on it, and it's a surface that's pushing perpendicular to the table. So if this is the table, the normal force is perpendicular. If you angled the table, the normal force would still be perpendicular, so that means it would go at an angle like this. One common misconception is that normal force is always up, and that's not true. Another misconception is that normal force is always equal to gravity. So if you look at that textbook example there, you see that the normal force and gravitational forces are equal to each other. And that is true some of the times, or even maybe most of the times, but it's not necessarily true. If you go over to that textbook and you push down on it, you would be adding a force going down, so then the table would have to exert an even larger normal force to keep that book from being pushed through the table. So that's just one example. Another example is if you tilted the table, the normal force would change as well. Many times an applied force is actually just a normal force from a hand or an object. So we're not going to talk about applied force in this slide, other than to say that applied forces are mostly just normal forces, because when you apply a force, it depends on how you apply it. Are you applying it by pushing on it? Then it's probably a normal force. If you're applying it by, bringing a magnet near it, then it's a magnetic force, etc. Tension. Tension is a contact force, usually through ropes, chains, or strings. And the thing about tension is that it always acts along the rope. So if you have a rope going like this, friction can only act left or right. Tension can only act left or right. If you have a rope going like this, tension can act only up and down. And the other thing is that tension can only pull. You can't push with a rope. You can't push with a string. So this is something to think about. Oh, tension is capital T, so F capital T. Elastic forces. It's also a contact force, usually through stretchy materials or springs. An elastic force always acts opposite of the direction that the object is stretched or compressed. So if you look at the spring on the very right, when you compress it, it's pushing back out against you. It's resisting that change. And if you were to stretch it out, it would want to snap back together, so it would exert a force in the opposite direction. So if you pull it out, it wants to snap back in. So the force is always acting opposite of the displacement or how you're moving it. That's called a restorative force. We're going to talk more about elastic force later. And then finally we have drag. Drag is a contact force caused by molecules in the air or the water hitting into an object. This is where you would see your air resistance force or air friction. The reason why I use drag instead is because we can also include other things besides air, like water or anything else you might be moving through. Drag always acts opposite of the direction, just like friction, but it's like air friction or fluid friction, I guess. The reason why I include water is because think about it. If you try to run through the water, you ever try to run in a pool, it's really hard because you're fighting all of those molecules as you run. You're bumping into more than thousands, millions and millions of molecules. And those molecules are exerting these tiny little forces on you that add up to a big drag force. Many times drag is negligible. I've had some AP students get so wrapped up in including drag in everything because they want to be absolutely right 100% of the time. But just remember that just because drag technically might exist in every situation that there's air doesn't mean that it's worth including on a free body diagram or a force diagram. If it's really tiny, then we would just ignore it. So we would call that negligible. Just means you can ignore it. And actually this is the last slide. I added this slide on actually after I taught some of you guys, so I forgot this one. So buoyancy, which I use just F-buoy, it's a contact force as well, caused by a pressure difference or a difference in density. If you get to AP Physics 2, you'll learn all about how buoyancy works. But for now, just understand that if you have an object that is less dense than something else, it's going to experience a significant buoyant force. And that buoyant force always acts upwards in a fluid. So whether you're in air, water, gas, or other liquids. Many times buoyancy is negligible, but in times where it counts, things like balloons, things floating in water, if you try to push a beach ball down underneath the water, it pops up. That's from a buoyancy force. So that's just something else to note. That's my last slide here. Sorry, actually, I have some extensions that this would be more for honors and AP level. So I will actually go through this, but before I do, if you're conceptual or advanced, you want to cut it off here, I just want to mention that you are required to understand and to know what all these forces are, what all these forces mean, and they're short abbreviations like FD or FF or FT. Those are the things, that's the reason why I'm showing you these slides, so you get familiar with where these forces appear and how to use them. All right, real quick with AP, guys, there's actually only 4 forces. And I know I just went through and I explained, probably about 7 or 8 of them, but there's technically only 4. One is gravity, which we did talk about. The other one is electromagnetism, which is magnetic and electrostatic forces combined. And then 3 and 4 are the strong nuclear force and the weak force. And those two are really weird, and they only really come into play when you get really small on the forces of atoms and all of that. So we don't really go into that very much, but all you need to know is most of the forces that we just talked about are actually electromagnetic forces because of the electrons in the atoms repelling each other. Like if we're talking about a normal force, right, the reason why my hand doesn't move through my other hand is because the electrons in my hand are repelling the electrons in my other hand. So that's really what's going on, but that's a lot more complicated to think about. Also, and that's kind of just what this is all about here too. So I'll let you guys investigate that on your own. That's it. So remember, you're responsible for knowing what the forces are, how they're abbreviated, and where you might see them, and in what directions they're acting. That's really what's going to be crucial to you understanding some forces stuff, just some foundational stuff. Thanks.